this wonderful new institute. So as Mana said, I was asked to give some introductory lectures to quantum optomechanics. And I've written here a selective introduction, so selective in many ways. So first of all, I'm a theorist, not an experimentalist. So I'll emphasize some of the theoretical aspects of this field. If you wanted to hear about how to do vibration-isolated experiments and dealing with the complexities of laser phase noise, you won't get that from these lectures, sadly. And the other thing that makes this sort of selective is, I guess I've been working in this area of quantum optomechanics for roughly 10 years. So probably a lot of the stories that I will tell you will skew towards things that I've been involved with, people in my group have been involved with over the years. So the rough plan of the lectures, and I will see how far we get through them. In this first lecture, I want to sort of start things slow, so give you a motivation to the field. Why is it that this area of quantum optomechanics has kind of exploded in the last 5 or 10 years? What are the big questions that people are going after? And then also in the first lecture, give you a flavor of some of the very basic theory used to describe the phenomena in this field. So in the first lecture, I'll focus on the mean field linearized theory of quantum optomechanics, the kind of theory that describes almost all experiments that have been done in the field so far, where there's a large laser drive, you're dealing with lots of photons, that makes the interaction easier to deal with. And I'll talk about things like dynamical back action. So probably the biggest thing there is the idea of cavity cooling. So basically using light to be able to cool some large mechanical object to close to its quantum ground state. So in the second lecture, again, if we're on time, I'll switch to what is maybe the holy grail of quantum optomechanics, and that is, could we actually get to the regime where the optomechanical interaction, the radiation pressure interaction between light and matter, actually matters at the level of single photons and single phonons. So that's a regime where we could have very large mechanically induced photonic interactions, photonic nonlinearities. It's a difficult regime to get into. I hope to give you a flavor of some of the recent work from my group and other groups where you can play tricks to actually enhance these kind of quantum nonlinearities. So by driving your system in just the right way, by parametrically driving the mechanical resonator, you can actually enhance these mechanically induced interactions. And in the last lecture, again, if we're staying on time, I'll tell you another kind of fascinating thing you can do in optomechanics as in other systems. And that's the idea of actually using the dissipation in these systems as a resource, the idea of reservoir engineering. So I'll tell you some work, both theory and experiment, where these ideas have actually been implemented in optomechanics. So the idea that you can use dissipation to stabilize quantum squeeze states of some large, massive mechanical resonator. The idea that you can use dissipation in optomechanics to actually do something strange, have non-reciprocal interactions between quantum systems. Interactions that only go in one direction. Okay, so again, that's the plan. We'll see how much of it we actually get through in these 3 lectures. If there's something crucial that you wanted to hear about and that's missing from my list, don't hesitate to let me know. All of this is easily changeable. And also just to start things off, I'll mention some references if you're new to this area of quantum optomechanics, good places to sort of get a nice introduction. So there's this Reviews of Modern Physics, I think it's called Cavity Optomechanics, from Marcus Aspelmeyer and collaborators. It sort of gives you the state of the art of the field in 2014. Luckily, it's a fast-moving field, so there's been lots of additions to the field since that time. But it's a really nice place to sort of get a quick introduction to sort of the main topics here. Similarly, there's a book, which is basically a collection of chapters by many different practitioners in the field, also edited by Marcus Aspelmeyer. And in terms of the basic theory, there's some chapters in this book from Springer, by myself, by Florian Marquardt, by Clemens Hammer, that gives you some of the basic quantum optics style theory that's used to describe these systems. Other references of interest, so a lot of the theory I'll talk about in this lecture is kind of the input-output Heisenberg-Langevin equation approach to describing these systems. A very quick and compact introduction to that formalism is in this Reviews of Modern Physics that I wrote with Michel and others. And an aspect of the field that I won't really spend a lot of time talking about is the quantum measurement aspect of optomechanics. If you want to hear more about that, My lecture notes from this Les School in 2015 are now available. Okay, so lots of material to hopefully complement what I'll be presenting in these slides. And so before I get started, it might be helpful to know how many people here are actually students or postdocs? See a lot, okay, that's good. How many people know something about optomechanics already? Okay, I see a lot of the experts who know about optomechanics, good. So I'm gonna start with a really nice, gentle introduction. It's Monday morning, it's 9:30, I'm jet lagged, and we'll gradually build up into sort of actually doing some more hard work, right? Actually building up the theory. Okay, so let's start with the big picture, the general motivation. What is quantum optomechanics? So at its heart, it's a subfield of both quantum optics and I guess condensed matter physics. It's interested in understanding the interplay of three very basic ingredients. We want to understand the interaction of light with mechanical motion, the motion of some large mechanical structure, so not really a single atom or an ion, but something involving billions or trillions of atoms. And we want quantum mechanics to matter. So when you put those three things together, what comes out of that interesting mixture? Right? Are there interesting resources that come out of mixing those three things together? And I think it's always nice to realize that thinking about this mixture is really something that goes back to the very beginnings of quantum mechanics. So I think in my mind, what I'm describing here is maybe the first Gedanken experiment in quantum optomechanics. And so this is a Gedanken experiment that was described by Einstein in a very famous lecture he gave in 1909. And the title of the lecture, okay, here it is in German. My German is not so good. It's something like On the Conception of Radiation. So it's 1909. We have the Planck distribution. We have Einstein's description of the photoelectric effect. People are still uncertain in terms of how to think about light. Is it a particle? Is it a wave? Is something else? So in this lecture, Einstein describes a kind of ingenious thought experiment. So imagine a cavity that's filled with thermal radiation, so thermal photons. And imagine inside the cavity is a mirror that's harmonically suspended, so we can move. Okay, so the first thing that Einstein says, okay, look, light is going to be reflecting off of this mirror. Light exerts forces on this mirror. So the idea of radiation pressure, right, this is already well described by Maxwell in the 1860s. So when the light reflects off of this mirror, there's going to be a Doppler shift of the reflected light K prime with respect to the incident light. That Doppler shift depends on the velocity of the mirror. Right? To conservation of momentum, that means there's going to be an impulse delivered to the mirror that depends on velocity. So there's going to be a force on the mirror that depends on velocity. So what's a force that depends on velocity? That's just a damping force. Okay, so the first thing Einstein points out is in this simple setup, the fact that the light is bouncing off this moving mirror, that's going to give you what we now call optical damping. The light is going to serve to damp the motion of the mirror. Okay, then Einstein goes on to say, well, wait a second, that can't be the whole story, right? Because if all the light did was damp the motion of this mirror, if the light is in thermal equilibrium and the mirror is just damped to stop moving, right, it's not going to be at the same temperature as the light. So clearly there's something missing here. What's missing? Well, associated with this optical damping, there also has to be a fluctuating Langevin force associated with this optical damping. So these impulses delivered from the light to the mirror will also give a noisy force on the mirror, and that's going to be responsible for keeping the mirror in equilibrium. So what Einstein does, so this is now the fluctuating part of these radiation pressure forces. So the real point of Einstein's talk is to calculate what those fluctuations are. And so in a really kind of ingenious calculation, just using the Planck distribution, he calculates the statistical properties of this fluctuating noise. And he shows that it has both a classical part, what we'd expect just from having random waves, and it has a quantum part. It has a part where the fluctuations, the variance of these forces is proportional to the average. It has a part that looks like shot noise, what we'd expect for discrete particles bouncing off the mirror randomly. Okay, so here we have it, the first Gedanken experiment in quantum optomechanics. It already has some of the themes that are important to the field even now. Okay, so what do we have? We have light kicking around a mirror. The quantum aspects of the light matter to the motion of the mirror. The light acts as a kind of dissipative reservoir for what the mirror is doing. Okay, so again, this is 1909. We We jump forward 100 years or so, and we go now from the realm of Gedanken experiments to real experiments. So this same basic interplay of light radiation pressure forces interacting with mechanical motion is now relevant to a variety of different experiments, spanning orders of magnitude in terms of the mass of the mechanical resonators involved, the frequencies of the mechanical resonators involved. And so these days, probably the most famous example where optomechanics plays a role is in gravitational wave detection. So here's a sketch, or here's a photo of the LIGO observatory, this large kilometer scale interferometer where you have suspended kilogram scale mirrors. So the optomechanics here, the fact that the light is kicking around the mirrors, causing them to move, this of course is a huge headache, right? This is what's going to be responsible for imposing quantum limits on how well you can make a measurement in this setup. In LIGO, it's crucial to understand what those quantum limits are, coming from the quantum light kicking around the mirrors, and finding ways to reach those limits, or maybe even surpassing the kind of naive limits you might think about. So down here we go to maybe more human scale experiments. So this is a more typical kind of optomechanical experiment. This is an image taken from Dirk Baumeister's lab at UCSB. So this is a cantilever that basically has a mirror glued onto it. So for these more lab scale optomechanics experiments, you're talking about mechanical frequencies that go anywhere from the audio to the microwave, so kilohertz to gigahertz. So mass scales anywhere from picograms to micrograms. So again, masses that correspond to billions or trillions of atoms. If you just work out what's the scale of the 0-point motion, so if you could take this center of mass of this cantilever, put it in its quantum ground state, how big is the uncertainty in the position? Well, again, you've got this enormous mass, some reasonable frequency. You get something like a femtometer, right? So the width of a typical nucleus. So the amazing thing is that scale, this 0-point scale, is actually relevant to experiments that are going on right now. Okay, so let's get a little bit more, towards getting a little bit more quantitative. So the idea is to have light interact with mechanical motion. The simplest kind of structure you could imagine is I have this suspended mirror that's free to move, and I bounce a laser off of it. Okay, so clearly if I bounce the laser off of this moving mirror, there's a force exerted on the mirror. There's also a phase change associated with the mirror depending on the light, depending on the position of the mirror, right? That changes the path length. Okay, so there we have the basics of optomechanics. The light affects the mechanics affects the light. But of course, this is just incredibly weak. If we're talking about some massive moving mirror, a single bounce is not going to do much, right? So what's the trick? We go from optomechanics to cavity optomechanics. We need the light to interact with that moving mirror many times. We add another mirror, right? So we make a cavity out of this structure. So now that cavity is going to confine the light. The light's going to bounce off the mirror many times. That's going to enhance the optomechanical interaction. Okay, so I'm a theorist. We have to get to a Hamiltonian eventually. So let me show you the basic Hamiltonian of cavity optomechanics, the one that's going to come up over and over and over again throughout these 3 lectures. So again, what do we have? We have this fixed mirror. We have this moving mirror that's glued to this cantilever. We're going to focus on just one resonant mode of this Fabry-Perot-like cavity. It's going to have some photon lowering operator A. We're going to focus on just one resonant mode of this vibrating cantilever, the center of mass oscillation. It has a position x, which I can write in terms of phonon operators, B and B dagger. Okay, and so to derive the Hamiltonian in the simplest way possible, I'm going to assume the experimentally relevant case where the mechanical frequency, again, at best, I don't know, hundreds of megahertz, is enormously small than the spacing between the optical modes. So in that case, we can take a kind of adiabatic picture to write down the Hamiltonian. So what's the Hamiltonian? Well, we just have 2 harmonic oscillators, right? The light in the cavity, the number of photons times the frequency of the cavity. We have the mechanical resonator. Its resonance frequency is omega m, the number of phonons. And now the simple idea is, well, look, when I change x, I change the length of the cavity. I change the frequency of the cavity. Okay, so that's my basic starting Hamiltonian. And then let's make it even simpler. typically the scale of motions we're interested in, right? Scale of these position changes on par with the 0-point motion, tiny, tiny changes, much, much smaller than the length of the cavity. So these changes in frequency coming from the motion of x are tiny. So whatever this dependence is here, I can just Taylor expand that, right? And just keep the first term in how the cavity frequency depends on x. So what am I left with if I then rewrite everything in terms of these raising and lowering operators? I have my two uncoupled harmonic oscillators, the photons in the cavity, the phonons in the mechanics, and I have this simple radiation pressure interaction. Again, this is just coming from the fact that the position of the moving cantilever sets the frequency of the cavity. Okay? And what is this fundamental single photon, single phonon optomechanical interaction strength? It's basically set by how strong does the cavity depend on changes in x times the size of the 0-point motion. Okay, and so in most experiments, this is a very, very small number. Okay, it's very small compared to the dissipation scales in the problem. So it ranges from maybe tens of hertz to, if you're doing really, really well, maybe you get up to close to a megahertz. Okay, and that's the basic Hamiltonian we're going to be playing with. Not really Jane's coming, so if you want another analogy, if you were, like I used to be, more of an electron person than a boson person, this exactly has the form of an electron-phonon interaction. So the simplest kind of electron-phonon interaction would be the coordinate of your phonon couples to the charge density of your electron. So this is kind of like the zero-dimensional version of that. Okay? So again, it's fair to ask, okay, this all seems very reasonable, but how would I derive this rigorously? And at one point I thought of going through that, but there's so much other interesting stuff to tell you. So I'm going to point out the reference, a really, really beautiful paper that really treats this system completely rigorously. That is, don't start by assuming you have a single mode in the cavity. Worry about all the modes. Worry about the problem of how do I do quantum mechanics when I have a moving boundary condition. So it's the same kind of problem and the same kind of theory that you need to use if you're trying to describe, let's say, Casimir-type physics. And again, in this rigorous kind of derivation, you see that there are all sorts of other terms I would have to add to this Hamiltonian if I was in a regime where the mechanical frequency and the spacing between the optical modes was actually not zero. Okay, so that kind of Doppler physics I told you about earlier in that example from Einstein, that shows up there. Okay, the reality is in all of the experiments of interest, mechanical frequencies are so, so different than the kind of optical or cavity frequencies we're talking about. Those other terms don't really play any role. So this kind of adiabatic approximation is incredibly well justified. Okay. So we have this, yeah, Michelle? Well, okay, so it depends on the way that the way you want to do your bookkeeping, right? So there's always, and again, this is really discussed very well in this paper. Depending on how you move things around in terms of making different unitary transformations, one man's Doppler coupling is another man's radiation pressure coupling. There are specific terms that depend on the velocity of the moving mirror that could cause scattering between different resonant modes of my optical cavity. There are also terms that depend on the velocity of the mirror that would correspond to like dynamical Casimir effects, right? So the ability to create pairs of photons. All of those are dropped when I get to this point here. Okay, so here, and this follows from we could talk about this more, yeah. So we should talk about this more, but so even if I think about this, go back to this Einstein example, right? So I talked about the Doppler shift here would actually give you a little bit of optical damping. This is not the same mechanism that dominates now when I go to a cavity and I get the same optical damping from, from having a cavity. So, okay, we'll talk about this more, yeah. So the idea is that this simple Hamiltonian now, this radiation pressure coupling, A dagger A couples to B plus B dagger, it really describes an enormous variety of systems. Okay, so these whole zoo of systems that people study in optomechanics, again, ranging from these gravitational wave detection systems to these more lab-scale optical cavities where you have some mechanical degree of freedom. Maybe it's the breathing mode of some toroidal optical cavity. Maybe it's a membrane that you've stuck in the middle of a Fabry-Perot cavity. You can even realize this kind of physics in a circuit. So take your cavity to be a resonant superconducting LC circuit, okay, and maybe the mechanical motion will modulate the capacitance in that circuit. That also gives you this kind of coupling. So many ways, so many experiments realizing what seems to be such a simple Hamiltonian. Why is this something that people should be trying to look at? Yeah, Manas?
G is of the order of 1 megahertz, right?
Okay, so this is really, really system dependent.
Right, but that's
the best
scenario.
Yeah.
And mechanical frequency and cavity frequency are also in megahertz. Is it couple of megahertz? Or?
Well, okay, so if we're talking about optical cavities, we're talking about hundreds of terahertz. If we're talking about some of these circuits, we're talking about maybe approaching 10 gigahertz.
But then it's like extremely weak coupling, right?
Extremely weak coupling. And so that the whole point of my second lecture is going to be, despite that incredibly weak coupling, how do I get something that is still quantum and nonlinear? What I'll tell you about in this talk is the simplest way of getting something. This coupling is really weak, but A dagger A could be made really big by putting lots of photons there.
No, I guess my confusion is the mechanical frequency.
Yeah.
What is the range of the mechanical frequency?
Oh, so typical mechanical frequencies in these kinds of systems, you're talking about, a few megahertz. Yeah.
I see. And then the cavity frequency depends on what you're doing, right? Optical or...
So it sounds like what your question is, it's a question about, okay, is this coupling really weak? And what do you mean by weak? What we'll see, we'll make that a lot more precise. The thing that's going to be most important is how big is that coupling compared to the dissipation rates of the problem. At the end of the day, that's the thing that you can't really get away from. Okay, but that's something we'll definitely spend some time on. Okay, so the simple Hamiltonian, it describes many different systems. Why is this something worth trying to study in so many different ways? Well, again, the basic interplay I already talked about is there in this Hamiltonian. One part of the interplay is the mechanical motion influences the light. So as X changes, it changes the frequency of the cavity. If you send in a laser near resonance on this cavity, the phase shift of the reflected light will depend on the position. So by measuring the phase shift of the light, you can make a position measurement. And these systems are basically able to approach the fundamental Heisenberg limit on how well you could continuously monitor a mechanical position. Okay, that basically corresponds to being able to resolve the 0-point motion of the mechanical resonator in a time comparable to the ring down time of the mechanical resonator, the time set by its damping rate. Okay? The other aspect in terms of how the mechanics affects the light, well look, if I imagine treating this interaction to second order, right, just do second order perturbation theory, right, I create and destroy a virtual phonon, that's what this diagram here is supposed to indicate. What will I end up with? Well, I'll end up with a term that's G squared divided by the mechanical frequency, A dagger, AA. Okay, so if you're an optics person, you would call this a kind of Kerr nonlinearity. The cavity frequency depends on the number of photons in the cavity. More of a condensed matter person, you'd say you've induced some kind of Hubbard view. Okay, so the idea is that the mechanics can make the light interact, make photons interact. This connects to Manas's question. So here you see, okay, this interaction is, is bad squared with something bad in the denominator, right? So G is really small, we square it. And then we put this mechanical frequency. Again, mechanical frequency, typically megahertz. This little g, typically hundreds of hertz. The induced interaction here you get is tiny. Okay, so one of the central problems, which I'll really try to tell you about in the second lecture, is how do I have this interaction matter despite this seeming tiny, tiny scale here? Are there tricks I can play? Okay, yeah. In this kind of simple system, you can't. Okay, so the interaction here, and we'll talk more about that, is attractive. If I now think about some more clever geometries, there are other things that you can do, right? If I selectively introduce another optical mode. Oh, so I just chose to write this in a normal ordered way, right? Sure, you could write this in terms of number operators, yeah. So the other aspect of this Hamiltonian is let's look at the physics from the point of view of the mechanical resonator. From the point of view of the mechanical resonator, anything that multiplies x in a Hamiltonian is a force. So in this case, the force on the mechanical resonator is proportional to the photon number in the cavity. That is the radiation pressure force. So the idea is through this coupling, through this interaction, we should be able to control the state of the mechanical resonator using the photon field in the cavity. Okay, so this will be a way, the first thing we'll talk about is cooling the mechanical resonator down to the ground state, even though its frequency is small, right, in temperature units, much, much, much smaller than room temperature. So that's the other aspect of this Hamiltonian that is definitely of interest. The light gives you a way of controlling the mechanical resonator, and ultimately, what would we love to do? Could I use the light to actually stabilize the mechanics in some sort of truly quantum mechanical state? Okay, so that's like the very basics of the basic Hamiltonian of optomechanics, a zoo of systems that are described by that Hamiltonian. You still might wonder, okay, why really spend time focusing on this field, on these kinds of systems? Everyone in this field will give you a different set of answers. So I've put down a couple of motivations that I find kind of compelling. I always tell this the same way. So I've listed them in the order of the more concrete to the sort of more speculative, or equivalently, these are things you could tell a funding agency and they will give you money. These are things you tell a funding agency and they will take your money away, right? So the field gives you lots of different options depending on what you're after. So clearly, one concrete motivation is this idea of sensing, right? So by having forces drive the motion of the mechanics, using the light to then detect it, you can make incredibly sensitive measurements that opens doors for new kinds of detection. So certainly gravitational wave interferometer is an example of that. People have built accelerometers, other kinds of optomechanical detectors. Just jump to this. There are applications to quantum information processing, which I think are pretty fun. So one thing about optomechanics is mechanical motion you can really make to couple to anything. So it'll couple to light, that's what I've been telling you about. Here's a kind of a very crude schematic of an LC circuit where this wiggly thing here is meant to be one plate of a capacitor that can actually vibrate. So I could basically couple mechanical motion to microwave photons, the excitations of this circuit. I could couple it to spins by putting a magnetic particle on a cantilever. You can couple mechanical motion to anything. So if I could get a mechanical resonator to be close to the ground state, that might be an excellent way of actually being able to move quantum information between very different kinds of systems, so a kind of quantum bus. Okay, and so this crude cartoon here is showing a kind of setup where the motion of a mechanical membrane, that's this squiggly thing here, could be used to couple and move excitations between a microwave cavity. So the microwave cavity is this resonant LC circuit, that's our L, two blue things here are our C, and between an optical cavity. So here, this membrane is basically a moving dielectric in the middle of this Fabry-Perot cavity. It is also going to change the cavity frequency as it moves. And so this kind of cartoon physics of being able to turn microwave frequency photons into optical photons, the first experiments exploring this physics have actually been done. So experiments in Boulder from Konrad Lehnert, Cindy Riegel's groups. There are experiments in Chicago from David Oshlom and Andrew Cleland. And there's some fun things to think about here, even from a theory point of view. So one of the things that we've been looking at is, okay, so can we use a mechanical resonator to move photons from one kind of cavity to another? Can we do that without actually having to put the photons, the excitations, ever in the mechanics? So there are these beautiful ideas from atomic physics, adiabatic passage techniques, what people call stirap, where you kind of do this amazing kind of shell game where a state starts here, it ends up in cavity 2 without ever spending time in the middle system. You can play those kinds of games in optomechanics as well. Okay, so one of many motivations driving the field, this idea of using mechanical motion as a kind of quantum bus. Sticking to applications in quantum information processing, you could also think about using the mechanics as a way of preparing interesting quantum states, despite the fact that the coupling is so incredibly weak. So here I'm going to tell you two fairly recent experimental implementations of this idea. The first is the idea of using mechanical motion to generate squeezed light. Okay, so again, we talked about the fact that, yes, it's a weak effect, but the mechanical motion makes photons interact. It makes the cavity frequency effectively depend on the number of photons in the cavity. So what that means is if I start with this optomechanical cavity, I send in just an ordinary coherent state of light. And so this blob here is representing the vacuum fluctuations of the light. Because of the interaction with the mechanics, if I play my cards right, what comes out is actually this noise blob actually gets distorted. Okay, and so this is squeezing. So formally, if I'm thinking about the light field at one narrow frequency, some narrow bandwidth, I can basically think of that as a harmonic oscillator. The x-coordinate of that harmonic oscillator would tell me about one quadrature of the light, so cosine omega t fluctuations of the light. And so this squeeze state of light is basically about getting the fluctuations in that quadrature, that direction in phase space, to go below the vacuum level. Okay, and so what's shown here is actually an experiment that was done in Cindy Riegel's group. We're using this optomechanical interaction, kind of very ordinary Fabry-Perot cavity, a mechanical resonator, a membrane. Its frequency is on the order of megahertz. They were able to get a reasonable few dB of squeezing. Okay, so I don't know, 1, 2 dB of squeezing, reduce the vacuum fluctuations in the light by 70%. Okay, so that's one thing you can do. Another thing you can do, this is now an experiment in microwave cavity optomechanics. This is from Konrad Lehnert's group. So here the cavity is this superconducting LC circuit. This is the PowerPoint version. So one plate of the capacitor is your mechanical degree of freedom. Again, resonance frequency, a few megahertz. This is what the thing actually looks like. Here is your capacitor where, again, one plate can vibrate. And what they were able to do in this system, despite this incredibly weak interaction, by driving the cavity in just the right way, they were able to entangle the mechanical motion with pulses of microwave light, leaving this LC circuit in a transmission line. So you can harness this optomechanical interaction to generate entanglement. You can entangle the mechanical motion with outgoing microwave light. You can even use this system to entangle two time-separated pulses of microwave light leaving the cavity. And again, I'll tell you a little bit more about how do we go from the Hamiltonian I described to you to being able to do these kinds of things. And again, despite the fact the interaction is so it depends, right? What constraints are you going to give me? So this kind of squeezing here, this sort of the simplest kind of optomechanical system that I described to you, in terms of how much squeezing you can get, the squeezing is very, very strongly frequency dependent. It depends on the detuning of the laser that you drive the cavity with. And ultimately, it does depend on the size of the optomechanical interaction. Okay, so it's not just that little g I told you about, which you can't really tune. It's also how hard are you going to drive the cavity. So the bigger the coherent state you put in, the more squeezing you can ultimately get. Okay, so in a few slides, see how many slides it is, I'll tell you about something that's known as the optomechanical cooperativity parameter. Right? So we talk about the interaction being small or weak. That's a little bit vague, right? That the interaction has dimensions, right? I want some dimensionless measure of is the interaction big enough to do something interesting. So it's this cooperativity parameter that's going to tell us about that. And the nice thing about the cooperativity parameter is you can always make it bigger by just driving your cavity harder. Okay, so the upshot is if you drive really, really hard, in principle, you can get more and more and more squeezing.
This is related to, of course, the fact that you have a negative U Hubbard model, right?
So it's actually, okay, so the simplest way of thinking about it, how do I get this kind of distorted ellipse in terms of the noise? I'm kind of correlating amplitude and phase fluctuations. That's a way of thinking about, Why is this circle now an ellipse, right? One direction would be amplitude fluctuations, one would be phase fluctuations. They're correlated. If you have this Kerr nonlinearity, this U, that will naturally do that. It's more complicated here because this nonlinearity is not instantaneous in time, right? So where's the nonlinearity coming from? You put light in the cavity, the mechanics displaces because of that, because the light is a force. And when the mechanics displaces, that's a change in its frequency. That doesn't happen instantaneously. So to understand the squeezing, it's really important to keep all of the dynamics. It's not completely identical to just saying, hey, I have this interacting cavity, this Kerr cavity to begin with. Okay, and that, depending on your taste, is either a good thing or a bad thing. It means that the phase of this squeezing, so what direction is the circle squished in, that's strongly frequency dependent. For some applications, that's a really good thing. For other applications, that's a terrible thing. Sure, so that would almost be the topic of a completely, general talk. So I can pitch it this way, right? So what are the advantages of thinking about using mechanics? The idea that in a simple way, mechanics can really couple to a wide variety of different things. What are the big challenges? The coupling is really, really weak, right? So you typically have to play tricks, drive the system very strongly to get the coupling big enough to do something. That driving can come with other problems, right? There can always just be heating associated with that. The other issue too is, is the mechanical dissipation really going to be low enough to prevent corrupting your state when you kind of go through this? So in terms of this specific, so the thing that people have really been focusing on in optomechanics is this problem of going from the microwave domain to the optical domain. So take information in a superconducting qubit, get propagating photons in a fiber out of that. There are other approaches that people are thinking about. So people are thinking about just using direct electro-optic nonlinearity. So just use materials that have the right kind of intrinsic nonlinearity. Could you just use that to get the same kind of physics? So I think right now, the answer isn't clear, right? Is this really the best thing to do? People are exploring many different avenues. This is a promising avenue. And the flexibility of these systems that ultimately we could really do this, mechanical motion could couple to anything. That would be a nice path forward, right? But that's not, I cannot tell you right now with a straight face, this is definitely the best way to solve this problem, right? I don't think anyone really knows what the best way is.
The first thing is about the squeezing. I think the model is kind of like really simple. So usually like in a cavity, you usually have two degenerate photon states. Like for a fiber-parallel cavity, they are carrying different spin angular momentum. And my point is that the squeezing really depends on how the electric dipole in the electromagnetic field and acoustic and the vibration mode, and also coupling together, and also the magnetic dipole, because this constitute the X and P of them.
So, okay, so yeah, so again, this was just really meant to sketch the fact that squeezing can be done. I haven't given you enough to understand it rigorously. The one thing I'll make clear is that there's nothing complicated in terms of the coupling you need. This simple system here is enough to already give you the squeezing effect. I don't need to tell you anything else about the coupling. There's a good question of asking what sets the squeezing angle, right? What picks out what direction I squeeze in?
Yes.
To get this squeezing, you're driving the cavity very strongly with a coherent state. So once I do that, I've picked out a direction in phase space. I've picked out the amplitude quadrature, and that sets the reference for, what's the orientation of this squeezed ellipse. Okay, so you are picking a direction in phase space by choosing to drive the cavity with a coherent state, right? A displaced field in a particular direction.
Yes.
What the optomechanical interaction is doing is basically correlating amplitude and phase fluctuations, and that sets the direction of this. But in terms of the interaction you need, it's just that simple optomechanical interaction, nothing more complicated. Maybe I'll tell you more about the squeezing, not this lecture, later on.
So my second question is actually the light matter interaction here. If you consider mirror, I think from optical aspect, it's not optimization for the interaction strength. You can, in many cases, like to use some sub-wavelength cavity mode and to make it really more sensitive to the vibration motion of the mirror or some kind of directional material in the system.
So you're thinking of, so one of the nice things about what I'm telling you here is that at the end of the day, look, there's lots of complicated details if you really wanted to understand any one of these systems in all of its specifics. The nice thing about optomechanics is that for all of these systems, all of the information on what the interaction is really just sitting in this Hamiltonian, right? So there's actually a lot of detailed physics in actually understanding, how do I understand what this little g is? If I wanted to actually calculate that from first principles for some real structure, it's a little bit more complicated than this Fabry-Perot model I've given you, right? So in addition to this kind of radiation pressure coupling, you also have to worry about, well, look, if I have some mechanical displacement, I have a strain field in my, my material, I'll change the index of refraction. That mechanism will also contribute to what I'm calling little g. It shows up in the Hamiltonian the same way as this kind of moving boundary contribution does. Okay, but the nice thing is all of those details, yes, someone should probably worry about if you really want to know the value of little g. Once you know, right, what the value of little g is, this interaction tells me what the dynamics is. So all the specifics are buried in that one little constant. Okay? It gets more complicated if you're in a system where many modes matter. You can certainly add complexity to this. But to me, it's really nice that a variety of systems, I can just describe with this simple Hamiltonian, and this simple Hamiltonian is enough to give me some really interesting phenomena. And you'll see that more as we go through the lectures. Okay, questions are great. So let's see, we're still motivating things. On this list, going from the more concrete to the more speculative, the last thing I wanted to talk about was something that I feel is a really interesting direction and is definitely beyond what is doable in experiment right now. And it's the idea of, could we actually think about doing new kinds of many-body physics with optomechanical systems? So one optomechanical cavity, where you have a cavity and a localized vibration mode, is great. A lattice of those would be even better, right? So as a theorist, you can't stop me from taking one optomechanical cavity, orange blob is the cavity, blue is the mechanics, using PowerPoint, making a lattice out of that, writing a Hamiltonian that describes my PowerPoint figure. So imagine now each site is one of these optomechanical cavities with this radiation pressure interaction. And imagine my photons could hop from site to site to site. Okay, so the question is, what would the physics of that kind of system be? And again, if you're coming from the condensed matter world, this looks exactly like the kind of simplified model we would write down for the electron-phonon interaction. So in the condensed matter world, if the photons were electrons, this would be the Holstein model. So the idea is in optomechanics, you could realize an all-bosonic version of the Holstein model. Okay, so it's more complicated even than that, right? So photons are not like electrons. Photons are not conserved particles, right? So if I ever wanted to do an experiment on this kind of system to get some kind of photonic population, it's always going to be some kind of driven dissipative system. I'll be driving the system to put photons into it. That'll be balanced against some loss. What would be the many-body physics of that kind of driven dissipative system? Okay? And this is not just complete PowerPoint animation fiction. There are steps to being able to realize this. So clearly, if I took some large, millimeter scale Fabry-Perot cavity, you're not going to be building an array of 1,000 sites out of that. Luckily, there are kind of nanophotonic approaches to realizing the physics of an optomechanical cavity. Okay, so what's shown here is a kind of, it's a planar photonic crystal. So imagine I'm looking down on a thin membrane of silicon. It's been patterned with holes, so these snowflaked, shaped white regions are where the silicon has been etched away. So this forms a photonic crystal. If the pattern was perfect, I would have bands for my photon propagation in this material. And now what do you do to get your optomechanics? You basically create defects in this photonic crystal. So a defect is a missing snowflake, okay, a missing pattern of holes. What that does is, just like a defect in a solid will localize a level in the band gap, the same thing happens in these photonic crystal systems. So each defect is like a localized photonic cavity. It turns out the exact same physics that gives you a band structure in localized modes for the photons in this system, the same thing is true for the elastic waves. So the same physics that localizes a photon on one of these sites also localizes kind of localized phonon mode. Okay, so this is work that was really pioneered in Oscar Painter's group at Caltech. A defect in one of these photonic crystal systems is a cavity. You now imagine building, and Oscar has, a superlattice of these defects. Well, then this tight binding model with this interaction is not such a crazy thing to think about. Okay? And yes, it's true that this interaction is very weak. So one thing that me and others have been thinking about, if you drive this system very strongly, put lots of photons in it, that's a route to having this interaction matter more. So in that regime, and we'll talk about this in more detail, what can happen is, when you strongly drive the system, your two harmonic oscillators can hybridize. So your phonons and your photons, right, they form new normal modes that are mixtures of both. So kind of hybrid light-matter interaction. I'm going to use the word polariton to call that. Hopefully no one gets upset. And these optomechanical polaritons in these structures, you could really imagine controlling their band structure by controlling how you choose to drive the system. Okay, so Florian Marquardt's group, we've done some work in this direction as well. You can get topological band structures and topological edge states for these photon-phonon polaritons. Okay, so there is an interesting kind of many-body, potential many-body direction to go in these kinds of systems. Okay, so this motivation is taking longer than I expected, but that's great, and the questions have been good. The last thing on this list I'm not going to talk too much about. Maybe this is best discussed after dinner or something. One of the other interesting things about optomechanics is potentially this is a nice, maybe even tabletop venue where you could do experiments where both quantum mechanics and gravity play a role in the same kind of setup, right? So there are ideas that maybe gravitational effects for fundamental reasons give you a kind of decoherence mechanism if you tried to create a superposition, a quantum superposition, where you have a massive object in either one position or another position in the two states. And the idea is that maybe in an optomechanical setup, you would be able to test for these unconventional sources of decoherence. Okay, so it's a very interesting speculative direction to be looking at. I would take this as a really, really, really long-term goal. Before you start pinning down unconventional decoherence, you better understand all the conventional decoherence mechanisms out there. But it is something that's really motivating some of the work in the field. So stepping back and just looking at this list, I think one of the nice things about the field, and one of the nice things about conferences in this field, is that you have people who are interested in these systems for very, very different reasons, whether it's gravitational wave detection, really concrete sensing applications, quantum information. They're all speaking the same language, more or less now. They're all going to the same conferences, exploring the same physics. And so that's been it's been a lot of fun for me just to, learn about different things through the context of optomechanics. Okay, so that was the introduction. So now I promised that we would start to make things a little bit more concrete. The equation density will hopefully go up. Let's see. So let's try to build up a bit more of a formal description of these systems, a quantitative description. And the first thing that I need to tell you about is, okay, there's more to life than a Hamiltonian, right? The systems we're dealing with, even my optical cavity, I need some way to get light into the cavity, right? The mirrors are not perfectly reflecting. I need to think about how my cavity talks to all of the light modes outside of the cavity. Okay, so I need to think about the open system physics of my optomechanical cavity. And the method I'm going to tell you about to begin with is a bread and butter method in quantum optics. This is the method of quantum Langevin equations, or Heisenberg-Langevin equations. Okay, so here again is our system. So now I'm going to worry about the fact that let's just focus on the cavity for a second. This mirror is not perfectly reflecting. There's a coupling between the localized modes inside the cavity and all of the modes outside of the cavity. Okay, so that coupling is going to lead to some damping of the cavity. That damping rate is what I'm going to call kappa. And the regime where most of these experiments are done, the regime in which we think about dissipation in quantum optics usually, is the simplest kind of regime for a dissipative problem that you can matter. And the idea is that most of the details of the bath, the source of the dissipation, just don't matter. So we can reduce it just to a few parameters and make the bath as featureless as possible. Okay, so the idea is that all of the physics, the biggest energy scale in the problem is this cavity frequency. That's enormous. All of the physics of interest is occurring within frequencies that are much, much smaller of the cavity frequency around that area. I only care about what's going on in the bath near that cavity frequency. So what I'm going to do in treating the bath modes, I'm going to take the bath modes, the modes outside of the cavity, to be a bunch of harmonic oscillators. I'm going to take those harmonic oscillators to have a completely flat density of states. Okay, so this is the extreme Markov bath limit. Okay, so there's one number characterizing the density of states of the oscillators, not a function, just a number. And then at the same time, what's the interaction between the localized photon mode in the cavity and the modes outside the cavity? It's this simple tunneling interaction, right? If you want this kind of rotating wave interaction where a photon can hop into the bath or vice versa. Okay, I don't need to keep the non-rotating wave terms, things that might be like A dagger, B dagger. Why? The dissipation is going to be weak. The cavity frequency is enormous. So even if you kept those other terms that you might do if you were worried about strong dissipation effects, in the regime of interest, that's just going to play no role whatsoever. Okay, so in this regime where the dissipation is so simple, we can derive fairly simple equations of motion just focusing on operators inside the cavity. Okay, so the first thing that we do is from this Hamiltonian for the bath oscillators, this simple linear coupling or bilinear coupling to the cavity mode, I can derive an equation of motion for the lowering operators of the bath mode. I see right away that there's a missing symbol in this equation here. So solving the Heisenberg equation of motion for these bath modes, the first term here was supposed to be the term, right, that describes what happens if there's no coupling whatsoever. So of course, if there's a hat on the left-hand side, there better be hats on the right-hand side. So I'm missing some B, Q, hat, not, right? So the solution of the equation if there was no coupling whatsoever. And then, again, all these harmonic oscillators are driven because of this term by the cavity. In this limit where the density of states is just a constant, that driving term here gives me something that's completely local in time. Okay, so basically by making this approximation of this infinitely flat density of states, the way that the cavity drives these bath modes is completely local in time. Okay, so we're going to end up with a description of just Markovian dissipation. So now what do I do? Okay, I've solved the equation of motion for the bath modes. I'm basically going to just plug this in to the equation of motion for my cavity mode A. Okay, and when I do that, what I end up with is this Heisenberg-Langevin equation, the quantum Langevin equation. What's that, sorry? I'm going to come back to that. I'm going to treat the dissipation of the mechanics in exactly the same way. So right now I'm focusing on this H kappa, which is the dissipation of the photon modes. We're going to do exactly the same thing. We then describe the dissipation of the mechanics. Okay, so big difference, right? So the coupling that was quadratic in the A modes was this radiation pressure coupling. This comes from the fact that what I'm describing here is purely photonic physics. This is the physics of having a leaky mirror, right? And if you want a quantum picture, the photons can tunnel out and they can tunnel in, yeah. So what's the structure of this Heisenberg-Langevin equation? The first term is just...
if you go to, just to be clear, like, so you made the rotating wave approximation here, right? This kappa over 2 pi rho should be small, kappa should be small, for that to be valid, for A dagger, B dagger terms to be neglected. So can you tell us what exactly it should be smaller than, because this is in the problem, and I'm sure same problem will happen with the mechanical mode. You will have the same kind of rotating wave approximation that you have to do. So can we just sort it out, like what should be smaller than what?
Let's start with just the sort of the photonic part of the problem. What I'm eventually going to do is basically go into a rotating frame at the cavity frequency. So all of the frequencies of interest are going to be in some window around the cavity frequency, right? And so all these frequencies of interest that are basically omega cavity plus minus something, and that something is small compared to the cavity frequency. All of those frequencies should be much, much, much bigger than kappa, right? And formally, that's if you imagine, right, the poor man's thing you would do if you wanted to then treat the non-rotating wave terms, you treat them perturbatively, right? The parameter that would control that perturbation theory would be this kappa scale divided by, again, the smallest of these frequencies that matter. Okay, and in our case, all of those frequencies are pretty much going to be close to the cavity frequency, because the cavity frequency is so much bigger than anything coming out of this interaction, that the cavity frequency being much bigger than kappa, your photonic mode having a high Q, that's going to be good enough, right?
Gapless, suppose omega Q goes soft, then you cannot do rotating wave approximation.
The problem is all of the physics is at this enormous frequency, which is the cavity frequency, right? So the bath could be gapless, but I'm never going to see that, right? I'm always seeing what's happening near this enormous frequency. The tail of my Lorentzians that make it down to zero frequency and see whatever that power law behavior is, that's such a negligible effect here. Yeah.
Really doesn't matter for rotating wave approximation.
And I think the philosophy here is important, right? Look, this is all coupled harmonic oscillators. I could add the non-rotating wave terms. It's still coupled harmonic oscillators. Why don't I do that, right? Why am I being lazy at this step? You don't want to keep track of more things than you need to. Why keep track of things that ultimately will play no role whatsoever? That ends up obscuring the physics you're actually interested in, right? And so once you know that, look, yeah, there are simple things I could still have kept track there, but they're not going to play any role. Why not start from the outset with a description that really just focuses on what the important physics is? So here, yes, there are lots of dissipative problems where you're not in this kind of nice regime and you need to worry. Even here, I'll try to point out some places where some of the standard approximations can break down. But the fact that we're dealing with an enormous cavity frequency, a really, really large quality factor, this is a really, really safe starting point. No, so right now what I'm doing is let's just focus on the damping of the cavity that's coming from the fact that this mirror has a transmission that's not zero. So if I start with photons in here, they can leak out, and noise, vacuum noise from these other optical modes can enter in. Let's just focus on that, come up with a description of that. Once we have that, we'll treat the damping of the mechanical mode, whatever the dissipation sources for the mechanics are, we'll treat it in exactly the same way. And I'll justify the approximation in exactly the same way, that my mechanical resonator has an incredibly high quality factor. So all of the physics from the point of view of mechanics is near its resonance frequency. What the bath does over some much wider range of frequencies is just not important. Okay, so this is the really weak damping limit of this dissipative dynamic. Sorry, which frequency? Sorry, okay, I'm now realizing too that there's an unfortunate choice of letters here. These B's here are supposed to be bath modes, photonic bath modes. They have nothing to do with the mechanics, right? So it's always in retrospect you realize that you just made a bad choice. Yeah. No, so here, these omega Qs here, right? These are describing really a continuum of frequencies. The way I'm going to describe them is with a density of states, right? As opposed to telling you all of their frequencies, there's a function that tells me where do I have an omega Q, where do you not have an omega Q. And that density of states function is completely flat, okay, over essentially all frequencies. Okay, so this is basically, I'm telling you that the details of the bath don't really matter. It's wide bandwidth and as far as you care, over the frequencies that matter to your cavity, that density of states looks constant. Okay, and that's going to give me a very simple description to go forward with. Okay, so we end up with this Heisenberg-Langevin equation of motion for just the photon field. So this is just, of course, what we would have if we just had closed system dynamics, if I forgot about the bath. When I plug in, again, this equation with the appropriate term there, into the equation of motion for the lowering operator A, this term here, the bath modes are driven by A, but then the bath modes themselves, of course, drive A. That's what's going to give me damping. So I have this simple amplitude damping, right? D by dt of A goes like minus kappa over 2A. That's the damping effect of the bath. And this term here, which is also an operator, all of that stuff together, when it enters the equation of motion for the cavity lowering operator, I'm just going to call that something. I'm going to call that root kappa A in. Okay, and just the way you would think about a Langevin equation classically, there's some damping, well, fluctuation dissipation tells me there's got to be some noise associated with that. So this term in solving these bath equations of motion is this noise term in this equation of motion. And how am I going to think about that? I'm going to tell you its statistical properties. Okay, so this thing, this guy here, on average it's 0, but if I look at its second moments, it's non-zero. Okay, it's describing the noise that's driving the system. So the first thing you see is if you look, so first of all, these are operators, so I've got to worry about the difference between A in dagger, and vice versa. Okay, the first thing you see is that they're delta functions in time. So these are like the operator equivalent of white noise. Why is it white noise? Well, I started by saying I have a completely flat density of states. So being infinitely wide in frequency space, infinitely narrow in the time domain. And then if I had just vacuum noise, this would be 0, and this would just be a 1. Okay? If I have thermal noise that's entering the cavity, that's probably not so important for the cavity, but when we describe the mechanical resonator the same way, the mechanics is definitely going to have thermal noise driving it. To include the thermal noise, we put in these Bose-Einstein factors. Okay, so here too, you might start to worry. You would say, well, wait a second. If I think about the thermal occupancy of these bath modes, how many thermal bosons BQ do I have? Well, it depends on their frequency, right? So then why am I throwing that all the way here? This is just a number, right? There's no frequency dependence here. It's just a number. It's the Bose-Einstein factor evaluated at the cavity frequency. Well, it's the same kind of approximation I've been making throughout. In this weak dissipation regime, all of the action is really close to the cavity frequency. The only bath modes that really matter are close to the cavity frequency. I don't have to worry about the fact that the number of thermal bosons is a function of frequency. I can just evaluate that thermal factor at the cavity frequency. Okay, so the description I end up getting once I do all of this, right, is this Heisenberg-Langevin equation where I have a damping term, and corresponding to that damping term, I have this operator value noise that's driving the system. Okay? And then with the mechanics, we can describe it in exactly the same way. So for the mechanics, I'll have some, and that's this B mode, the mechanical B mode. I would also have some damping term. Do I write this on the, this not yet. I'll have some damping term, and I'll have some corresponding noise term. Okay, so let's move on. So we don't want this leaky mirror just to be a way for photons to leave and for noise to come in, right? We also want something good to come in through that mirror, right? So we also want to have a laser in our system that is putting good photons into the cavity. So how could I describe that? There are two equivalent things I could do. I could just put a linear driving term in the Hamiltonian. So now this A bar in of t, this is a time-dependent complex function, right? So this is the amplitude of the driving laser. Equivalently, that's like just taking this noise term here and giving it an average value, right? Exactly the same thing. Okay, so that's how we're going to account for the coherent driving of our cavity, just linear driving. It's It's not going to be so important for this problem, right, or for what I'm going to be telling you about, but often we really care not just about what goes into the cavity, we care what comes out of it. So unlike what you do in a lot of open quantum systems problems, we don't want to completely trace out the bath. Because at the end of the day, what you measure as an experimentalist is in the bath. So if I just trace it out, integrate it out, I can't describe what you'll actually measure. So what we also care about is, if you want this blue arrow here, what is the field leaving the cavity? Okay, and so a nice way of thinking about our Markovian bath is this picture that's sketched here. Let's think of my Markovian bath, the field outside of the cavity, as basically a chiral, a one-way, photonic waveguide. So photons are coming in. At some point x naught, they interact with my cavity mode, and then they zip out. Okay? And so what I care about is, after the interaction with my cavity mode, how has the field changed? Okay, so the field just after this point x out is what I'm calling A out. The field just before it is the same thing I had written here. It's this input noise. And the relationship between those two things, it's actually like solving the problem of a delta function potential, right, in Quantum Mechanics 101. The difference between those is you just integrate up that delta function coupling. The output field is the input field plus this term that has to do with what the cavity is doing. Okay, so the physical way of thinking about that is, if there was no coupling to the cavity, which here means there's no kappa, right, there's no tunneling, then everything is just reflected, right? Whatever comes in just bounces off. The output field is the same as the input field. Once I have a coupling to the cavity, there's more stuff coming out, right? There's stuff inside the cavity that can leak out through this mirror and also contribute to the output field. Okay, so that's a more physical way of thinking what that equation is telling us. Okay, once we have this, then we can not worry about the bath anymore. We can kind of integrate it out. Okay, we can still tell the experimentalist what they will see outside their cavity. Okay, so some other standard transformations. So the most simple case that we'll consider often is just monochromatic driving of the cavity. So I'm going to drive the cavity with the laser with a fixed frequency, omega L. I'm going to write its amplitude in terms of this alpha L parameter. Okay, and a convenient thing to do is to go into a rotating frame where I get rid of this explicit time dependence in that driving field. So there's a unitary transformation that will get rid of the driving, that explicit time dependence in this driving part of the Hamiltonian. When I make a time-dependent unitary transformation, there's this extra term that shows up when I'm transforming the Hamiltonian. So at the end of the day, what happens when I do this transformation, my Hamiltonian no longer has any explicit time dependence, right? This driving term, just I get rid of that exponential factor. But now my cavity frequency basically gets shifted by whatever this laser frequency is. So in this rotating frame, I'm basically measuring the cavity frequency with respect to the laser frequency. So I'm going to define the detuning as the laser frequency minus the cavity frequency. And so the cavity frequency, the A dagger A term in the Hamiltonian, is now just minus that detuning. So this is one of these places where there's actually a caveat here that hopefully we'll get to in lecture 2. This is not completely innocuous. So if you do this carefully, right, if you do this carefully, you should really go all the way back. Well, we should actually think about this bath cavity coupling as well. So if I'm going to do this shift to a rotating frame where my A and A dagger operators will pick up time dependences, I should also shift all the bath oscillators so this system bath coupling doesn't become time dependent. Right? So who cares? The bath is some abstract thing. I can shift its frequencies. If I have a constant density of states and I shift frequencies, it's still constant, right? So what's the big deal? Well, there is a big deal, right? Whatever my bath was physically, there were no negative frequencies to begin with, right? That would be a problem. When I go into this, when I make this rotating frame transformation and I shift the bath frequencies, in the new frame, there are actually negative frequencies in the bath. Okay? So you need to worry about that for certain problems. The fact that in the rotating frame, it looks like you effectively have negative frequencies that means it looks like vacuum fluctuations can actually give you energy. Okay, and so this phenomena has many different names. I like this terminology, quantum heating, that maybe Mark Dickman was the first to really introduce. So that can lead to some very, very interesting physics. So basically, driving a quantum system can lead to vacuum fluctuations turning into real photons. And to account for that properly, it's really crucial to not forget that you shift the bath frequencies when you make this transformation. Okay, so, yep. So why don't you save that question for the next lecture? I'll go through that in detail, actually. Okay, yeah, and you'll see that coming into play, yeah. And really what it is, it's the combination of vacuum fluctuations and the driving that together give you real photons. Okay, just in this formalism, right, and the way we're doing the bookkeeping, right, that's coming about from having what apparently seem to be negative frequency oscillators in this rotating frame. Save the question for the next lecture. It'll be a lot clearer. Yeah, I'll explain what I mean in more detail. Yeah. Okay, so we're almost done. We need to make a couple more things to sort of make things a bit simpler. So the last thing we're going to do is to say, well, look, here is my Heisenberg equation of motion for the cavity field, right? I'm in this rotating frame. I have this constant term in the equation of motion. It's time independent, which is my coherent laser drive. And I have this noise term, the vacuum fluctuations that are coming into this leaking mirror. So the next thing we want to do is, let's basically eliminate this constant term in the equation of motion. Okay, and the way we're going to do that is to make a unitary displacement operation, right? If I had no optomechanical interaction, I drive my cavity with coherent light, I know I'm going to get a coherent state. I'm going to get a state where the average of A is going to be non-zero. Okay, so what I want to do is I want to make a transformation where I basically measure these operators, A, the lowering operator for the cavity, same thing, B, the lowering operator for the mechanics, with respect to these, these classical coherent state amplitudes. So formally, I'm going to introduce two new operators, canonical bosonic operators, D and B, usual commutation relations, that are displaced with respect to the original photon and phonon operator. And I'm basically going to pick these amplitudes here to just satisfy the classical noise-free equations of motion. Okay, so the classical equations remove all hats, right? Get rid of all the noise terms, so get rid of that term there. Solve those equations, right? That will give you these amplitudes that you want. So when I'm driving the cavity, right, even with the optomechanical interaction, I'll get some coherent state amplitude in the cavity. That's going to be alpha CL. If I put photons in the cavity, right, if A dagger A has some average value, that's going to be a constant force on the mechanics. It's going to shift its equilibrium position. So that's going to give me, that shift in equilibrium position will be this B bar CL. Okay? And so once I do that, so now I go into this new picture where I'm measuring everything with respect to these average displacements that comes from the field. And let's just skip that. We finally get the form of the optomechanical interaction that we're going to work with throughout the rest of this talk. Okay, so in the final, at the end of the day, we're in our rotating frame. We have these displaced photons D, these displaced phonons B nu, right? So here are their frequencies. The cavity frequency has been shifted by the displacement of the mechanics. There's this new detuning I'm calling delta prime. And now what does my interaction look like? Well, I started with A dagger A couples to B plus B dagger. So now when I expand that out using this formula here, I see that there's two parts to the interaction, right? There's a part that's linear in D and D dagger, and that's enhanced by this alpha CL. This is the classical amplitude in the cavity that I've induced by driving the cavity with a coherent laser. So that alpha CL can be very, very large if I crank up the laser power. And then I still have this quantum nonlinear part, the D dagger D. Okay? So, in the remaining 8 minutes, I guess, in most experiments in optomechanics, little g is tiny. We talked about its hundreds of hertz up to maybe a megahertz if you're really lucky. To really get an interesting interaction, you really have to drive the cavity strongly. So it's only going to be this first term here that matters. This term is negligible. This interaction term only involves little g. This term has little g enhanced by, again, this alpha is this ACL. It's enhanced by the square root of the number of photons you put into the cavity. So you crank your laser knob to 10 to 11, you get lots and lots of photons. This many photon interaction, gone from little g to big G, this could be big enough to do something. Okay, so at the end of the day, you could imagine making a kind of mean field approximation due to the weakness of little g and the largeness of your laser driving. The interaction you're left with is just this simple linear coupling between two harmonic oscillators. Okay, and one of the oscillators is your photons, this D operator. The other is your mechanics, this B operator. The nice thing is, though, you have control over this Hamiltonian. You have control over the size of G because you can control the amplitude of your laser drive, which sets the number of photons in the cavity. You also have control over the detuning here, right? You can choose the frequency at which to drive your cavity, which changes the value of this detuning. Okay, and that leads to two particular simple, versions of this interaction. So let's imagine the mechanical frequency is really, really large. The mechanical frequency is really, really large. You can go even further and say, look, it's two coupled harmonic oscillators, but that's still too complicated for me. I want to get something even simpler. So I can imagine trying to make a further rotating wave approximation on this Hamiltonian. So if the mechanical frequency is really, really large, imagine I choose to drive the cavity with a laser frequency that is red detuned from the cavity frequency. So the laser has a frequency less than the cavity frequency. It's detuned to the red exactly in amount equal to the mechanical frequency. So in that case, this minus delta becomes omega m. I have two resonantly coupled harmonic oscillators, right? So the terms that want to create or destroy a pair of bosons, those are massively non-resonant. The D dagger B and D dagger D terms are resonant. So the rotating wave approximation I get is even now simpler, or it gives me even a simpler interaction. So I have what in quantum optics terms you would call a beam splitter Hamiltonian. In condensed matter terms, maybe a tunneling Hamiltonian. I have a simple interaction that can convert a phonon into a photon and vice versa. And of course, at first glance, that seems crazy. Phonons and photons have very, very, very different frequencies. Why is this possible? That frequency mismatch is being compensated by this large drive laser that you've applied. So this is the kind of Hamiltonian that we're going to go on to use if we want to do cavity cooling. So for cavity cooling, the damping rate of the photon mode, this kappa, is sufficiently large that if I have quanta in the mechanical mode, they'll tunnel into the photon mode and rapidly dissipate. That's going to be the origin of cooling. This is also the kind of Hamiltonian you want if you wanted to do this kind of quantum state transfer, right? Have two very different cavities talk to one another through the mechanics. So having two copies of this interaction, I could start in cavity 1, hop to the mechanics, and then hop to cavity 2. And again, this interaction is controllable. You could turn it on and off by turning on and off that control Hamiltonian. Okay, so the other opposite regime is, again, mechanical frequency really, really large. You're going to make a rotating wave approximation. Imagine now I take my laser to be blue detuned. So the laser frequency is bigger than the cavity frequency. How much bigger? Exactly an amount equal to the mechanical frequency. So in that regime, this detuning here, this delta, is equal to omega m. So in this rotating frame, it looks like the photons have a frequency minus omega m. The phonons have a frequency omega m. So what terms here are resonant in this interaction? It's the terms that create or destroy pairs of excitations. So the rotating wave approximation you make here gives you this funny looking interaction that can create or destroy a phonon-photon pair coherently. Again, where is the energy coming from? It's always coming from the drive laser, right? We're working in this mean field approximation where the amplitude of the drive laser is buried in this big G. So this is the kind of interaction, we go way back to close to the beginning of the presentation, that can generate entanglement, right? So when this interaction acts, it generates pairs of phonons and photons. It will eventually lead to a state that looks like this. So this is what's known as a two-mode squeeze state, where the number of phonons is completely correlated with the number of photons. This is the kind of interaction that experiment I told you about from Konrad Lehnert's group, that they used to basically entangle the motion of a mechanical resonator with photons leaving the cavity. Okay, so these are two simple regimes of the optomechanical interaction. What I want to do sort of moving forward is, just because it's so important to this field and what's been achieved, I want to tell you in a little bit more detail how this cavity cooling physics works. Okay, I want to tell you maybe, so that's a story that maybe many of you know or you've heard about. I'll tell you maybe about a little bit of a wrinkle on that story, that here it looks like, oh, you need the mechanical frequency to be really large to be able to make this simple approximation. How large? Well, much bigger than the cavity damping rate, kappa. Right? Because once I have damping, energy becomes a little bit uncertain. Right? So if the energy is too uncertain, I'm not sure I can throw away the B-dagger, D-dagger terms anymore. Okay, so I'll tell you about an interesting kind of cooling. We're using interference effects. Even if the mechanical frequency is really small, okay, much smaller than kappa. So you can't make this rotating wave approximation. You're still able to cool all the way to the ground state. Okay, we call this dissipative cooling. There was an experiment just recently that actually got this to work. And then once we have that, maybe I'll try to get to the plan of the second set of lectures, which is what happens when we try to go beyond this mean field approximation. What if I really want to worry about these terms here? And there's two approaches, right? One is experimentalists are amazing people. Right now, this little g is tiny, but I'm sure give it a couple years, little g will get bigger and bigger and bigger. So all this great theory I'm doing surely will be useful to someone at some point. So that's a level of optimism that sadly I don't always have, right? So another approach is to say, well, look, little g is tiny, but I really want this term to matter because, look, I'm a theorist. I don't want to study coupled harmonic oscillators for the rest of my life, right? So how do I actually get that term to matter despite the fact that little g is tiny? Okay, and what I'll tell you is there's some interesting tricks in terms of how you choose to drive the system, more complicated than what I've described here, where this nonlinear interaction can still matter even though little g seems to be too small to make a difference. Okay, so I think with that I will stop and yeah, thank you.
Same thing will happen.
So okay, so you're talking about quadratic coupling optomechanics, which I didn't mention here at all, right? Which is, there's a clever way where you can actually, where do I write so how did I get this term here? I said the cavity frequency depends on x, right? So there are symmetry ways where if I put a membrane in a Fabry-Perot cavity and I align it just perfectly, right, at at an antinode, you can have that linear term vanish. So the cavity frequency only depends quadratically on x. And then the first term in this interaction would be A dagger A couples to B plus B dagger squared. So then a lot of the basic physics is actually different. The way of describing dissipation that I told you is still fine. Right? The quantum Langevin equations, you would still derive the same way. But the way that this radiation pressure interaction works is quite different. I can tell you maybe a bit more about that later, but the physics is definitely different. Yeah. It's a different nonlinearity at the end of the day. There's an extra B in that term.
So when you're saying that the G, the value of G is small or weak, at one point you also mentioned about this cooperative thing. So which is it this G square over kappa gamma? Like that's
so the and again, I meant to get to this, but things don't always go the way you plan, which is fine. The cooperativity that's going to matter for this Hamiltonian to be able to do something. So this Hamiltonian, I got big G, is basically how large is this thing compared to both the photon damping and the phonon damping. And the dimensionless measure, up to a factor of 4, is compare this to the geometric mean of the photon damping, which is kappa, and the mechanical damping, which I'm going to call little gamma. Okay. There's a very different question, though, which is, when does little g actually matter, right? And what's the dimensionless measure of that? And the answer to that question is it depends. What are you trying to do with little g? So that we'll talk about in the second lecture.
I have a question. This is about the rotating frame. My question is, I guess you'll get to this quantum heating later, but there is something you do usually here, which is there was a thermal factor, which you usually evaluated at the cavity frequency. And then, of course, you don't worry about it and you continue to do the calculations in this rotating frame. Is this work that you're talking about something more than that? That's also presumably not completely right.
But that's still okay, because if you want this, one part of this rotating frame is almost like a relabeling, right? So what I was calling a mode at some cavity frequency, I've just shifted what I'm calling zero frequency. So now omega equals omega cavity has been shifted to omega equals 0. If in the original frame, the bath modes at the cavity frequency had some thermal occupancy, in the new frame, again, it's just a relabeling, right? In the new frame, those modes are going to still have the same occupancy, but they're going to be sitting at a different frequency. So I don't really have to change the thermal factors. The thing I was talking about is a little bit different. It's the fact that in the new frame, you really do have some negative frequency oscillators. Okay, and so that gives you a way of processes that you thought couldn't conserve energy can now conserve energy. Terms like those, like that B dagger, D dagger, right? If I have negative frequency oscillators, I can create two things and conserve energy pretty easily, right? That's the issue that we'll have to deal with.
On the mechanical side, can you have can you have something else than just harmonic modes? Can you have nonlinear modes for the bees?
Yeah, and I think, there's even experiments that have sort of looked at that. I think the holy grail here, for at least, okay, I'm a little biased, I like H bar, right? We want quantum nonlinearities, right? You can have mechanical nonlinearities, Duffing type nonlinearities, like an x to the 4th term in your mechanical potential. To have those actually matter at the level of a few phonons, there's some thought that maybe things like graphene or carbon nanotube could ultimately achieve that, but it's really, really, really hard. So I'm not aware of any experimental system in this broad, field of optomechanics and even quantum electromechanics where people have really seen intrinsic mechanical nonlinearities that are important at the quantum level. People have looked at what it does in sort of more classical regimes. There's some interesting things. But again, the holy grail is nonlinearities that matter in the quantum regime. Yeah, so what happens at resonance, so when you drive exactly on resonance, is of course you need to, you need to keep all of those terms, right? Because there's nothing that tells you, when you're driving on resonance, it's like the photons have no frequency, right? So whether I, create or destroy a photon makes no difference, right? So both those terms, the beam splitter term, which is like the tunneling term, and this two-mode squeezing term, they both matter. A nice way to think about the resonant driving case is, hey, if delta or delta prime here is 0, the cavity has no Hamiltonian. So that means whatever this thing here is, d plus d dagger, it's a conserved quantity. So people sometimes talk about this as a QND regime. And so if you think about it, what does this d plus d dagger represent? It actually represents the amplitude fluctuations of the light. It's one quadrature of the light. So this idea, this regime where there's 0 detuning, this actually turns out to be a good regime to get this kind of squeezing I described. So the idea is that the mechanical resonator will measure the amplitude fluctuations of the light because the mechanics, B plus B dagger, is coupled to D plus D dagger. And then the mechanics will take that information and write it onto the phase quadrature of the light. Okay, so the interesting thing when delta is 0 is D plus D dagger is a conserved quantity. So there are interesting things to do in that regime. It's a good regime for position detection as well, if you're trying to measure the mechanical position. The requirement that we have a steady state. Yeah, so again, there is a slide that I thought I would get to, and we will get to it eventually. There's something I swept under the rug. I told you, okay, you're going to make this transformation. How will you get these average values? Take this equation, remove all the hats, and solve it. It's a classical equation. What could go wrong? Well, it's a nonlinear equation, right? So what can go wrong is you can have bifurcation. So there are regimes where you drive the system strongly enough, you pick the wrong side of the detuning, that your classical equations will give you multiple answers for steady states. And if that happens, everything I'm telling you doesn't work, right? Because now, which of those steady states should you really expand about? There are theoretical ideas for how you would extend these kind of techniques into this regime of bistability or multi-stability, but it's certainly more complicated. Okay, so the additional requirement when you're thinking about the mechanics as well is that when you solve the classical equations of motion, which are nonlinear equations, algebraic equations, you don't want any multi-stability. Okay, and that turns out to be a constraint that on the sign of the detuning and the strength of the laser drive.
Okay, so maybe one last urgent question.
What is the best cooling achieved till now, experimentally?
What's the best cooling? I think the best way, let's just see if I can, there's one slide that I stole from this review that shows this really nicely. We'll get to it soon.
In terms of phonon numbers,
so this slide actually shows you, so this slide is from this Reviews in Modern Physics from Marcus Aspelmeyer and Florian Marquardt and others. It was sort of the state of the art maybe as of 2014. And what this is showing is how much cooling have people achieved using the interaction with photons in the cavity. So this is the y-axis is phonon number, the starting phonon number to the ending phonon number. And this solid blue curve here this is the quantum limit on conventional cavity cooling, right? If you want, this is the quantum limit that comes from the fact that if omega m over kappa isn't infinite, your rotating wave approximation is not perfect. Okay, and there's actually one more thing to put on this. So this is maybe a very recent experiment from Cindy Riegel's group, where they start by using a dilution refrigerator to help get this 1 megahertz mechanical mode fairly cold. Then they do cavity cooling, and amazingly, they're able to get down to about 0.2 average phonon number, and that's actually pretty much exactly this quantum limit, given the fact that for their system, the mechanical frequency and the cavity damping rate are about the same. Okay, so that, you can find this in that Reviews of Modern Physics paper, but this gives you a sense of what people have achieved with this cavity cooling technique to cool mechanical resonators to the ground state. The one other thing is, of course, you could start by using a very high frequency mechanical mode, right? So something that's up in the gigahertz. Then you just stick it into a dilution refrigerator, and you're naturally going to end up with a very low number of phonons. This is all about starting with relatively low frequency mechanical modes, megahertz or even lower, and using these tricks of using light to actually cool things down.